Here. Okay, perfect. Okay. So, just to make sure that everyone is on the same page, you have the announcement on the blackboard about the questionnaire you have to answer regarding the two papers that you have to read. As if you have already read these papers, you will see that it's a kind of summing up of the things that we have been discussing in the introduction of the course. So the idea is that you get also the message. Do you listen to me? Are you listening to me? Okay, because I have an announcement here that, okay, saying that I have problems with my microphone. So please, if at some point you do not have a good audio, please let me know. Okay, so the idea is that you wrap up and have in black and white the different concepts and ideas that we have been discussing in the first sessions of the course. And then through the questions, the idea is also to make sure that you got the main message of the papers. That's one thing. And another thing is that anyway, in anything you decide to do after your studies, you will certainly have to work with text. And the idea is also to give you the keys on how to deal with technical text. Normally, we will be reading papers from trendy people, I mean, reference in the area, so that you can also see how ideas are put together, which are the right questions to be asked. And through the questions of the questionnaire, being sure that you didn't miss something when you were reading the papers. So just one comment, you have right only to enter once to the questionnaire. So once, if you open it and you register, well, I think that if do not commit, you can still come back, but otherwise, since the address is registered, you will only have the right to access once. So be aware of that. And again, well, I will at the once, well, the deadline is on Sunday, so you will receive a notification of the number of points that you got from the questionnaire. And but I mean, do not get a heart attack if you do not get all the points, or if you get few points. Again, I remind you that this is working material for the course. Okay, so it doesn't count in any note. Okay, it's just to make sure. Well, there is a percentage of the grade associated to the. Yeah, I mean, we will discuss this together after the deadline. I will go through the document to make sure that we discuss and you get everything out of that. But again, do not get a heart attack if you do not get many points. This is the way we learn. I mean, in fact, we learn by failing something or part of it, and then making sure, going back, and then making sure that we get all that was supposed to be there. Okay, so you will receive, of course, a percentage of the grade out of the readings, but the readings is doing. Okay, so if you do, you get your points, even if through the questionnaires you do not achieve a lot of points. Okay, so again, it's another way of of grading. So do not say, oh, I just get 1 over I don't know how many points, so I will stop this course because I'm doing bad. No, there's no possible way of doing bad in any of the either the theory or the practical course. Okay, so that's not possible. As long as you keep doing things and keep participating, and it's a circular and continuous way of doing things. Okay, so just to make sure that you get this. Okay, so today we are approaching smoothly, but with a strong pace towards more concrete aspects, and maybe aspects that for which you have much more background than those that have been discussed until now. So today we are going to start looking about on having a look to one of the main problems associated to big data, which is managing data, okay? Which are the tools that we can use in order to manage the collections that we have been discussing. So it is raw data that is heterogeneous, that is voluminous, that it's incomplete, imprecise, missing, contradictory, which refers to veracity, that is released continuously at different rates, and that has different conditions in terms of proprietary, critical, or privacy. Okay, so these kind of collections, in fact, are neither manageable nor exploitable as such. Okay, so we need to perform data management operations on top of it in order that we can exploit their content. And that's what we are going to address next. So this is something that we have seen before. So a lot of data distributed on different capacities, and then that has to be stored on different supports, persistence supports. I have discovered that you didn't have any course on storage support technology. So if at some point I am saying something that you do not know, please ask, okay? Do not think that I will be surprised or whatever because you haven't had input on some particular concept or problem. Please tell me, because many of these concepts are really the very basic and underlying things on top of which we are going to develop knowledge in this course. So it is very important that everything that I say is clear for you. Okay, so as I said, you can have local disks or disks sitting on your home, external disks. Then you can have farms of storage support that we call RAIDs, and RAIDs have specific ways of being managed in order to store the data. Or we can have externalize access to storage support, for example, in the cloud. And according to this changes with respect to the slide that we have seen before. What we have to consider in order to start reasoning about storage and about persistency is that, of course, the formats. That the formats have are key in order to start thinking about storage, because at some point we have to transform or to understand the characteristics of the formats in order to exploit the content. Okay, so different formats, different sizes, that's normal, different data storage support. So which are the criteria to be considered in order to decide to store something in one technology or in the other. And again, here I'm talking about the type of hardware we are going to choose to store our data. Are we adopting a classic disk with these plates turning with the braces accessing the plates, or are we using solid state support, or other kinds of supports, okay, flash memory, for example, this kind of thing. So that's another aspect to consider. And then which are the mechanisms that will deliver the data when someone or an application, I say someone in a very metaphorical manner. Here, there are almost never users. Okay? Here there are systems and processes and applications that are willing to access the data in order to be able to execute some task. Okay. We are, for a long time, we will be far away from end users. We do not care about them until we really want to deliver a cloud solution accessible to anyone. Okay, but since we are unboxing the cloud, for us, this is not important for the time being. And now, okay, so we have this decision-making problem. And then one thing that we have to consider if we really want to go into this decision-making about what support to use in order to store our data, well, there are three things that are the ones that have to be, that guide the decision-making, okay? So first of all, the notion of scalability. Okay, since we have a lot of everything, we have to think about a solution that scales. Okay, it's huge. And scalability in terms of always, it will be always the same. That's something that you are used to because you are studying computing engineering. But the three key elements that guide our decisions when we want to develop a solution or want to buy a machine or whatever is CPU, memory, and disk. And normally, well, across along the time, we have there has been the possibility of increasing performance in a very an easy manner and proportionally to added resources. Okay, so today we have access to supports that have increased almost smoothly with respect to our perspective. And then why do we want to scale? Because we want to improve performance. Okay, we are, in general, we will see eventually that performance is not the only criterion to make decisions, but in many cases, our decision is guided by performance, meaning that we serve more units of work for handling larger units of work, like when data sets grow. Okay, so that's something that you learn at the beginning of your education. When you reason about algorithms that will become programs and processes at some time, what happens is that they will be able to perform more or less right with respect to the amount of data they will have to process, and of course, with respect to the resources, CPU, memory, and storage, that on top of which they will run. Okay, and the problem here is how are we going to tune the execution environment with respect to the amount of data so that we can increase performance. Okay, so we are looking for the right architecture that will provide good performance given the characteristics of the data that we want to process. And then, well, during many years, what has happened is that if I need more resources, well, I buy a more powerful machine. And so I solve my problem. But the thing is that there is always a limit on the type of machine that you can access to in order to address your requirements. Okay, at some point you will get to the limit of accessing the most powerful machine possible, one machine, in order to increase performance. So the idea is that rather than buying the last or the future machine, powerful machine ever, what it is possible to do is try to scale up and scale out by adding resources with in a separate manner, okay? And so here, what you have to bear in mind with respect to the rest of the discussion is that we are going to talk about vertically scale up, which means adding resources, essentially CPU and memory, to a single node in a system. Okay, so if I need more space in my computer, I buy a larger disk in order to increase my storage support. And if I want more CPU cycles in order to run my programs, well, I buy a more powerful or an extra CPU so that my machine can be more powerful in terms of processing capacities. Okay, so that's vertically scaling up. Okay, and the other more flexible one is horizontally scaling up, which means adding more nodes to a system. So if I need more power, well, I buy another machine and I connect them together, and I treat my both machines as if it was one, and I increase my CPU and storage power. Okay, and if I do the same many times, I become Google. Okay, so the solutions of many vendors today is that they, even if they buy powerful servers, what they do is they increase their power by adding servers to their farms. Okay, and this is what led to the existence of data centers at some point. Do I have a question?
Yes. Excuse me. I wanted to ask, what would be the benefit of each, of vertically scaling up or horizontally scaling out? Which are the like the pros and the cons of each?
What do you think? What happens if I add more resources to one machine?
It
What
becomes
do I
better at
avoid?
it becomes better at handling large data sets.
Yes. Okay. Right. And so what? What do I avoid doing? Compare it with if I have two machines.
Say if you have two machines, if one fails, you still have another one, I guess.
Okay, so that's an advantage. And what would be a disadvantage?
Extra cost, maybe.
Managing cost. When I say I have to treat both as if it was one system, this means that I need the right operating system, that there will be communication cost. Okay. You have probably learned this in distributed systems. The critical aspect element in distribution is communication. So if I scale out, okay, I have different machines, but I have to make sure that their connection is of very high quality. That's one thing. And the other, I have to make a lot of decisions in what to put in which machine. Do I put my data in both machines? Do I deploy a server in machine A or machine B? So you increase the cost of management a lot. But on the other hand, if you have only one machine, you have a bottleneck. If the machine goes out, it goes out with all the resources that you bought. Whereas if you have two, if one is not working, you can always have another one as backup. Do you see the difference?
Yes, doctor. Thank you.
You're welcome. Okay. Now, and another thing that I never talk about, but has to be considered, is cost. If you, I mean, if you think about what I'm saying when I say vertically scale up, at some point you will end up with a mainframe, and mainframes are not cheap. They're very expensive. Okay, so, and maybe, I mean, if you imagine 10 machines, 10 normal machines, they might reach, if they're really powerful, the computing capacity of a mainframe, but 10 machines will never cost the same as a mainframe. And you need specialization and a lot of things. So it's a cheap way of having a lot of resources. You have also costs of energy. It's, well, I will try to organize like a kind of virtual visit to some HPC center, but one of the problems with having these powerful machines is the cost of energy associated to that. Okay, there are millions of euros to be invested in order to be sure that the machine is correctly connected, etc. And as you know, energy is a non-renewable resource. So that's another problem. Whereas if you have many machines, the cost at some point can be reduced. But anyway, the government still, government in the world still invest also in these powerful machines. Okay, so it's a question, it's a matter of what do you want to do with this, okay, and how, in which conditions you want to deliver the services. Okay, so there are pros and cons, and for the time being, the only thing that I'm saying is that depending on the possibility that we adopt, we will have to adopt also different data management strategies. Okay, that's the only thing. Okay, we are happy. We have either powerful machines, one machine, or either powerful farms of machines. And then how do we move from classic data management solutions into these new architectural settings? When in industry, and particularly in industry dealing with a lot of data, so vendors of information retrieval, observed that classic data management solutions were very good for dealing with some problems, but very costly for addressing other problems because of their characteristics, okay? And so started to emerge other data management strategies that were more adapted to two things: to modeling the data. Okay, so we started with raw data, as I said, and now we want to model the content in order that we can exploit it. Okay, so depending on the characteristics of the data, it was more or less difficult to model them in classic data models. Okay, so that was one thing. And the other thing is that in order to manage your data, you do not only have one, do not only need one set of guarantees with respect to your data management. Sometimes you can accept to have less costly and less complex ways of managing your data, because, for example, you only want to do a lot of reads and writes, but there is few concurrency and etc. So you do not need a complex system to manage your data. You just need something that lets you read and write on top of a farm of disks, for example, and then deal with the data in those conditions. Okay, so out of this observation, from industry started to emerge a trend called non-relational trend. Okay, so a lot of systems adhere to this non-relational trend, which is a family of solutions. Okay, and that opposed to the relational solution. Okay, this doesn't mean that the relational is null and that we have to forget about it. This just means that the relational is fine for addressing a kind of family of problems, of data management problems, but there are other management problems that call for new strategies in order to manage the data. Okay. Sorry. So out of that started, as I said, to emerge, well, the trend, and then a lot of systems that adhere to this. So here you have relational, here you have no relational. I will go into details in a minute. And then another thing that was that then came after this movement is that relational evolved to have a more flexible spectrum of data management than the classic one that you will have learned probably in your education. Now the problem is that since a lot of solutions came up, we ended up with this. So now we have huge number of solutions, of systems, etc. And what do we do with all this? Okay, so how do I decide which one is the best for what, etc. And well, there are three main things that you have to observe from these huge families of solutions that you have. Okay, the relational zone, and have a look that the relational zone is still very complex. Okay, there are systems more devoted to business intelligence, for example, others more devoted to process scientific data, banking data, etc. So a lot of things here. And then this is worse because this blue zone represents the non-relational zone. Okay, I will explain in a minute why. And then there was another zone. Do you remember that when we talk about storage, we are talking, in fact, about three elements that participate in a data storage and data management solution. This is the hard disk, whether it is distributed, it is arrayed, it is whatever you want, it is milk if you want. So anything, the storage support, the hard support, then the cache, and main memory. Okay, so these three little stack is the one, these are three components are those that will participate in a data management solution. Okay, so the question is which are the expectations and the characteristics of these three elements in order to provide a data management solution. So if we come back to what you know, which is the relational, at the very bottom of the stack, the relational systems have been conceived and designed in order thinking about classic storage disks, those that have the plates, okay, those that turn and have this arm in order to look for the records in the hard disk. Okay, so under this hypothesis of this hardware characteristic, they develop strategies in order to make the data come from the disk to cache and then to the data management system. Okay, if you open the data management system. Okay, so these three elements are important. Then if you go to cache, normally what you will end up with within the cache is pages, okay? And once you go up to main memory, in main memory, you will essentially have, well, either objects or either low-level representations of your relation, okay, of your table. Okay? And then you have in fact, you have records, okay? And then the application is fed with these records, okay? So you have this kind of solution. And then the DBMS, the relational DBMS, is designed such that it provides transparency with respect to the underlying hardware, as I have said before. So if you have a cluster of machines providing storage support, or if you are really accessing to a NAS, for example, with racks of disks, this is transparent with respect to the applications, well, the systems that use the DBMS. Okay, the DBMS hides all this complexity. And this is the beauty of the DBMS. One of the greatest, there are two great systems that we have came up as a community in computer science. The first one is operating system. It's a super great system solution that this is one of the greatest results of our domain. And the other system, which is great result too, is the contribution of our domain is a relational DBMS. Okay, so these two are key in history. Okay, so but anyway, they are not static. They have been evolving because of the evolution of hardware requirements, etc. So the relational DBMS has evolved too. But anyway, this is a great thing that to be understood and to be considered in order to understand how to go further. Well, once we said this, we have to figure out how are these relational DBMS going to evolve in order to address other aspects. And in fact, there are three elements to consider. First of all is the way we deliver the services of the DBMS. Well, first, a DBMS is a general purpose solution. It serves to build any application and, well, to design any database to any application dealing with data that are represented through a mathematical model, which is a relational model. Okay. Then they are normally used by specialists. So you do not suppose that an end user will use the DBMS. It's rather programmers and architects that will use this kind of solution. And it is possible to access this solution, its different functions, as services. Okay, so that's one thing. The other thing is the appliances and the way data go in memory. And then another thing is what are these relational models able to support? As we know, as we all know, they are able to model data as relations, as mathematical relations, but then the problem is that data is not always relational. Okay, there are data that is represented in documents or that is represented, for example, in graphs, and so the classic relational solution works poorly when it has to deal with this kind of data. Okay, so the idea is that we have to consider these three families of characteristics to try to go further or beyond the solution provided by the relational DBMS. The relational, well, you have also to think about these kind of systems as a market, okay? There's a lot of economy behind that is going on. The relational solution has been around for more than 30 years. Industry has invested in having relational solutions. So one idea was, if there are new requirements emerging, let's let the relational systems evolve so that they can respond and fulfill these new requirements. And there are three ways in which relational systems evolve in order to deal with new aspects, particularly in order to deal with data that was not naturally represented as relations. Now, just to be sure that we are on the same page, I remind you that a relation is the cross product, is defined as the cross product of a series of named domains, together with a set of integrity constraints that define the semantics of the relation. And there are specific characteristics of a relation, and then of what we call a relational schema. So a set of relations that describe a mini world and that are used in order to hold data related to a mini world, which is that every relation must adhere, and the schema must adhere to a set of mathematical properties, one of which that are called normal forms. Okay, so you remember, of course, normal forms. And so the thing is, in order to evolve the data model, we have to revisit these mathematical properties expressed as normal forms in order to make the data model, the data representation, more flexible. The first way that was adopted in order to address this evolution was forgetting about relaxing the first normal form. Do you remember what is the first normal form? And
No,
now you discovered that the normal forms were important. Yes, tell me.
no, I think, well, at least I do not remember what's the first normal form.
Okay, so first normal form says that every attribute of a relation must be atomic, okay, of an atomic type. An atomic type is the one that cannot be decomposed in further, it's not a structure. It cannot be decomposed in further elements. So integer, string, character, float, these are atomic types, and a relation, the attributes within a relation must be of an atomic type. So a column cannot be a structure. And how do we solve this? Because we decompose it and we denormalize the schema and have several relations. And we ensure that, for example, they are connected together. Okay, but first normal form is all the attributes of a relation are atomic. And now what happens if I need to represent non-atomic data? Well, as I have said, we decompose in many relations. And what is the problem of decomposing, of normalizing a schema? Well, of course, we gain a lot. We avoid duplicates, etc. But what is the problem, the disadvantage of having normalized schemata, relational schemata?
Maybe it becomes more like making queries and obtaining like results in general become like way more complex as you've normalized your database system.
And what is the kind of operation that you have to use in order to deal with this? You're right. It's just to complete.
Probably some joints.
Yes, joints are very costly operations. So if you have a normalized schema, if you have to maintain it, it reduces cost. But if you have to query a lot, you have a lot of joints to perform, and joints are costly, particularly if you have a lot of data. Okay, so that's first thing. And the second thing, I'm sure that you have experimented this, is that modeling a relational schema is time consuming, because you have to understand the mini world, and you have to understand the rules of this mini world and transform this into an abstract specification. And then once you have it, then it goes to your relational schema, and you have to make sure that it has the right properties, etc. And this costs a lot of time. And when you are in industry, time to market is a critical thing. Okay, you do not want to spend a lot of time in designing a database at some moments of your data management problems. Okay, so the first thing that it was thought to be done in order to ease this and adhere to more general problems was to evolve into extended relational models. And I think that given your age, you should have, in fact, used an evolved relational DBMS. And then you have advanced DBMS where you have learned that there are objects in relational databases. So having objects in relational databases is letting is stopping with the first normal form and letting attributes to be structures. Okay, so first family of solutions is what I have represented here. Is not only going, of course, it's the first normal form, and this touches types of data that are structured by themselves. One is spatial data, and the other is graphs. Okay, so with this evolution, then a lot of functions and architectures within internal architecture of the DBMS evolved. And so, for example, Exadata is a relational solution that it's made for OLTP is online transaction processing. Okay, so it's the kind of systems that you already know, the relational ones, guided by transactions. Okay, so they increase the performance of OLTP applications. They internally, they are deployed in rack configurations, and then they can deal with spatial and data and graphs as such. Another evolution is, for example, Hackathon. There, yes.
Yes, teacher. What is rack configuration?
A rack.
Yes.
In huge servers, I don't have an image. You see that there are black boxes like in Matrix or in films like that. There are black boxes with layers, physical layers, and inside they deploy the CPUs. This is a rack. Do you see what I mean?
Okay, yes. So they put there the CPUs? Okay.
Yes, so there are like these spaces where you deploy a lot of CPUs. And then the line is a rack. And so these boxes have several racks. And if you are processing data, you think about the racks, so you know that that some pixels of an image lay in rack number 1 of line number 2. Okay, so it's like a coordinate system that tells you where are the pieces of your data across the different racks.
Okay.
Do I have another question?
Thank you.
You're welcome. Is there another question?
No, I just sent a link to an image of a rack.
Ah,
Yeah.
good. Did you share it?
Yeah, through the chat.
Ah, yes, I see. Yeah,
Yes.
have a look at that. Thank you.
Yeah, you're welcome.
Thank you. Okay, so now there are other families, for example, Hackathon. There, normally, you avoid having in relational solutions, you avoid having data lying long time in memory. Why? If I have the data in memory for a long time, what can happen? What type of problem can come up? What is a characteristic of main memory, of RAM?
It's volatile.
It's volatile. And the problem is that I have to ensure durability. Do you remember the acid properties? One is durability. And if I keep data in memory, it's painful for durability. But what do I gain? Execution performance. Okay, if you want to go fast in processing, you need to have everything in main memory. So the problem is, how do you deal with this? Okay, so there are solutions that develop strategies in order to ensure that despite data lying in memory for long periods of time, they can still ensure durability. So they can go fast, but they keep the data in the conditions that with the guarantees they promise. So there are tables optimized in memory, and this is, for example, quite interesting for time series. Okay, if you are dealing with time series or with streams, you might need to have this kind of solution where you have in-memory data so that you can process your data continuously, and then at some point deciding what to store or not. Okay. And then if the data, if you have a lot of in-memory, another problem that can come up is concurrency. Okay. How are you going to let different processes access to the same main memory space without perturbing the consistency of your data? So they have this, and so this is another type of solution there addressing performance. Okay, because if you have a lot of guarantees, this is very nice, you are happy, but the overhead is enormous. Okay, so you might prefer going fast even if the solution does not offer a lot of guarantees. Okay, and so this is the guess that they adopt, for example, in Shaker. And then there are others. DB2, you probably have heard. DB2 is one of the major relational DBMS in the market today, and they have been working in order to address multidimensional solutions and evolving tables so that they have performance. Also opting for performance when they want to evolve their systems. Okay, so this is what you know. I started with what you know because there you can feel comfortable, you know, relational, you know, the characteristics of the DBMS. And now what happens? Well, it happens that, as I said, there are many applications where, I forgot to do something, or, yeah, this is why it's telling me that it has problems with my microphone because it cannot put the captions. Anyway, okay, so if you need to run reads and writes on thousands of millions of users, for example, if you're Google, then you need lighter solutions. Why? Because you are, in fact, you write very, you write, but you write very seldom, and you have a lot, you need to be performant in readings, okay, and answer to many user requests. So if you have such a requirement, a very simple requirement, a relational DBMS can be a monolith that causes a lot of overhead and provides you with, as I said, with guarantees that you do not really require. Okay, so the idea is how to provide a solution lighter that can exploit scaling out architectures a lot and in a very easily manner. Okay, you must know that, and you probably know that relational DBMS work, of course, in clusters and in scaled out architectures. The problem is that you need very skilled data managers, engineers that can deal with this. Okay, and here the purpose is to do not require such specialized engineering knowledge and still be able to scale out and provide light solutions, light management solutions. That's one thing. And the other thing is, if you, once you have said that, there are different aspects that you have to think about. For example, that is something that I said in the previous slide. What about the data model? Do I really need to represent everything in a mathematical model such as the relational model? Can I not imagine something lighter that I can still use in order to represent my data, but does not require such strict mathematical properties for the data to be modeled? Do I really need strict consistency in my data? For example, if we are, let's say that we use a Google Doc in order to write a report. Does it matter that I see that some of you start writing something and then delete and then rephrase something and go back? So these are dirty readings, but it doesn't matter to me because I know that we are working together, that you are thinking and you are producing this content, and that at some point we will decide whether this is the version, the content that we adopt, or if we still modify or whatever. Okay, so our requirement of consistency is very low. And isolation too. I would like to see what you are writing so that maybe I can have that I can, for example, adjust my ideas and ensure the consistency of thinking of the document we are producing together. Okay, so very low requirements of consistency and of isolation until a specific moment. Eventually, I will ask that the whole document is consistent. But in the process, I can accept low level of consistency. Okay, so if such applications are there, do I really need strong transactional properties or not? Okay. Do I absolutely need that all the data all the time go back to disk? Or can I accept that some data rely in memory, and if I lose them, or if I have other alternatives to ensure to go beyond the problem of volatility. Can I accept this, and rather than going back to this, because then I have swapping overhead if I go back to this every time. I have talked about durability, availability. Do I need all the time all the data available or not? And do I really need query evaluation support? Okay, what do you prefer, writing in SQL or some of the requirements that you need in order to process your data, rather writing a program rather than expressing some aspects of your queries in SQL? So that's a question. It depends. So out of this reasoning emerged what we call NoSQL databases. Okay, and at some point, many of them emerged. One of the most initial and the most famous ones that were, as I said, promoted by the main vendors and the main actors of computing science was HBase, for example, Neo4j, Redis, Cassandra. HBase, it was Apache, but at some point it was Google. Cassandra is Facebook, etc. So many different vendors started to come up with solutions. So what was the objective? Okay, let's build a new DBMS, and what are we looking for? Well, they were looking for flexibility, okay? No time invested in designing a schema. You get the data as it comes, okay? That's it. To be faster and cheaper, to be able to move to massive scales. This is, we will read an article of Michael Stonebreaker, and well, we will have the opportunity to discuss about this massive scale. Then, and lose consistency and prefer performance and availability. And think that at some points it is maybe more interesting to have to program more rather than have declarative solutions for expressing queries. So these were the guiding objectives that were back in the design of these NoSQL systems. Yes.
Yes, doctor. I have a question regarding loose consistency because like I cannot like understand what it means or how it relates to NoSQL systems.
What is strong consistency?
I think, yeah, I think that's like I cannot wrap my head around the concept of consistency. Also, what I think about consistency, I don't know if it applies, is for example, I don't know, a banking application that like you may have like your account balance and maybe, well, correct me if I'm wrong, but I would say that consistency in data would mean that in like every transaction or like whatever the data is accessed, like the bank account balance is consistent, meaning that it's the same value. But I'm not sure.
Okay, so that it's part of the answer. The first thing about consistency, it refers to your integrity constraints. Okay, you define a set of integrity constraints associated to a relational schema, and every operation that you perform on the database results in a new state of the database, and the state of the database respects all the integrity constraints that were specified. Okay, so you modify, and then the system goes and checks that all the integrity constraints are verified. So that's first thing to say about consistency. And the second thing is related, in fact, to atomicity. Okay, atomicity refers to the fact that you are going to perform a set of operations, and either you execute all of them or none of them. And how do you decide whether you accept a set of operations done on top of a database? Because the result of such operations lead to a database state that respects all your constraints so that it's consistent.
Oh, okay. So we could say that in a way, no SQL systems are like, I don't like, well, I think about them as maybe easier to implement or to maintain, because like as you said, you're not like
Right.
dedicating so much time on like on the logic behind the system.
Well, the first thing, if we go back and we put together these two elements that we have described now, if we think about integrity constraints, if you stop designing your schema, there will not be any integrity constraint. Okay, so first of all, the notion of a data collection, there is no notion of consistency for a given data collection. You can accept anything. Missing values, garbage, whatever you want, because there is no set of reference, of logic reference that to which the data must adhere. Sometimes there is no even type, okay? Because, do you remember? No, one of the first type of integrity constraint is the type. No, an attribute has a type, and so any value of the inserted in the attribute must be of type integer or real or whatever the attribute type is. If you stop doing this means that you can have names with one character, with a number, with whatever. No consistency in these terms, okay? In terms of data types. And of course, nothing about any other property. And so that's the first aspect of consistency. And the second is that you can accept intermediate states of the database that are not shared by everyone. And this is where your example of banking account comes to the matter. Okay, so you can modify your bank account, so you can take money out of the ATM, and you can go to an application and see that you still have the money, whereas in fact you had already deduced money from your account. Okay, but at some point everything will come to will be synchronized, and then you will see the final state.
Yeah, okay. Thank you, doctor. I think I understand now.
Yeah, and then we have a lot of examples of things that we do like that. I'm sure that you do online shopping. In online shopping, you have your cart, and sometimes what happens is that you add things to the cart, blah 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 blah, and you're happy you're there, and you spend 3 hours looking for the products, and now you're happy you have your products in your cart, and then when you validate, they tell you, oh sorry, in fact this is not available, but you were having a look at the product on the catalog, and this means that the catalog with respect to the database that really contains the effective products available at some point are not synchronized all the time. And we do not get angry. We just say, oh, bad luck, pass out of the cart, and then I buy the rest. Another example is if you google.com, you do google.com or google.fr, and you ask the same query. In fact, the results are not the same, because the servers here in Europe or in France are not all the time synchronized with respect to the servers in America. But we still can accept this. It's not critical, in fact. You see, so this kind of applications accept loose consistency.
Okay, okay. Thank you, doctor.
right? So ambitions, wrapping up, ambitions. So we are adopting less complex data models. And when you ease or you reduce the complexity of your data model, in fact, you are reducing the complexity of the type of applications yes, the type of operations that you can apply on top of your data models. This you have learned in data structures. The type of operation that you can apply to a buffer is not the same as applying the same complexity of operations that you can apply on a matrix. Operations in matrices are much more complex than on a buffer or a linked list. See? So here we are reducing the complexity of the data models, and thereby we are simplifying the operations that we perform on top of data. What are essentially what we're doing is we do key lookups, writes on only one record or in a small number of records. Okay, so very, very simple things to do. We stop thinking about complex queries, no joins, never in the life. So just lookups, looking for data by key. And then elasticity in the sense that we can dynamically add new attributes to the data records. That's something that you remember. If you want to modify the schema of a relational schema, of course you can, but this has implications on the data that you have already in the database. The database doesn't let you have inconsistencies, so you have to transform it into the data that you already have, the database, into the new schema, and this is very, very costly. Okay, so on the other hand, in this type of solution, you add a new attribute and you're fine because you have loose consistency. So you have some data that have a certain attribute and others, the pieces of the database that doesn't, and you don't care. Now, the basis is to have horizontal scalability, which means that you are looking for a system that will distribute the operations across the servers that it has access to. If another server comes and adheres to a cluster, it considers the new server in a kind of smooth manner. Okay. And how? Because these systems rely on no shared memory or disk. Okay, so every new server that comes is independent, and so if a new one comes, then new data will go to that server, but they are independent of the data already stored in the other services. And also memory, if you have a client connected to a certain server within your cluster, then it will read the data from this server on its memory, but then it will never share the same process cannot go to two memory spaces and think of it as an integrated one. And if you do this, you are going towards high performance. There will be a lot of distributed indices, a lot of storage in main memory, in RAM, as we said, with consistency and very limited transactions. So almost all properties that we knew in the ACID transactional model are not there. Okay. And now, what does it mean if you still have an application that needs, for example, concurrency control? What does it mean if you adopt this kind of solution? What happens?
in concurrent.
But you are, yes, so imagine that okay, I don't have a relational solution, so transactions are limited, and particularly, for example, concurrency control is not ensured. But my application still requires some operations to be done under a concurrency control model.
Well, I think in that case, wouldn't it be like troublesome? Because, well, if you are like in concurrency, isn't it, for example, if two users are maybe accessing or modifying the same piece of information? So if there's no like a strict way to like to prevent like the same data to be modified twice, maybe you could get to a point in your state in which like the users have modified the same thing and like there's no consistency
Yes,
in the information.
yes, that's a problem. And which is the solution?
Maybe if a user is accessing or using a specific piece of data, maybe like applying like a lock to that piece of data in order to avoid other users.
Exactly. And who is going to put the lock?
Well, maybe I do not know.
The programmer. You have to
Teacher, it's
implement
like
concurrency
no,
control.
it's like for
Sorry,
example, the programmer puts the lock by, for example, I don't remember the name exactly, but as in operating systems
two-phase,
of processes,
two-phase locking, or
semaphore,
yes, or the semaphores. Yes, yes,
semaphore,
exactly. But this is something that you have to implement as a programmer. So you didn't invest time in designing the database, but now you have to program a concurrency control solution in order to still provide this guarantee, because the underlying system doesn't provide you with this. Okay, so this is just to say that it's not that these systems are not to be used. The thing is that you have to be aware that if you have an application that doesn't have this type of concurrent access to the data, that there are a lot of reads, for example, and no write at all, then you can accept this, because there will never be a problem if two people are accessing the same resource, because the resource will never change. They will only access it in reading mode. Okay. But if you know that you have applications that will write at the same time that other read, then you have to think whether this is the right solution to be adopted in order to manage the data of an application. Very good. Yes, it's a good reflex that you see this. Okay, everyone agrees? Yes, and I forgot, I'm going to, I know that we have to wrap up. I'm going to end up here. Another aspect to be considered with respect to these non-relational solutions is that they are not submitted to a lot of standardization. Well, the relational is a very old solution, so there has been a lot of effort for standardization. So if you, for example, you know SQL3, SQL3 is the same in DB2, in Postgres, in Oracle, in MySQL, and whatever. Okay. So this is because it's the language is standardized. If you think of the architecture of the relational DBMS, it has a Nancy Spark architecture independently of the vendor. Whereas here, in fact, what happens is that there are specifications of types of systems, but the vendors decide what to adopt or not. And this makes the emergence of huge solutions of everywhere and for everything, etc. And the problem here is that if you are an architect, what is the solution that you are going to choose? You are not going to learn to use thousands of systems. This is not possible. Okay, so this is the counterpart of these families of systems. Until now, there still are a lot emerge, even if in the historical moment that we're talking, there are some that are really very popular, but there are still systems emerging. So here you have the reference of this, but I'm going to finish the session showing you, if I still have here. So this is the page that is referred there, is here. So it is a page where people have decided to think about the existing and to qualify them and to have like a landscape of NoSQL systems. And you know, for now, there are more than 225 systems in their list. And here you have all the systems with their description, with the company, the documentation, etc. But this is the arena, no? And we will see that inside the NoSQL there are families, but you know, here there are still people until 2020 that were working in this landscape of NoSQL systems, trying to compare and to give guidelines to engineers in order to not be that lost in this complex context of NoSQL systems. And so for the course, what we are going to do, it will be to use, I will show you and you will touch in the first part two examples of NoSQL systems. We are going to use MongoDB to show you some document-oriented solution, and then we will use Neo4j, which are two of the most well-known systems. Neo4j is a graph database, so that you can, you know, touch and have an insight on what these solutions look like and what we can do on top of them. Okay. So today there was a lot of talking. I will try to reduce my talking as we go further in the course, so that at some point you can also touch and we can play a little bit, so that it's not so much talking and more doing. Okay, so tomorrow we will go through these models and through these systems, trying to like wrap up tomorrow on the first touch of these NoSQL systems, so that we can move. We are increasing in scale. Okay, so now architectures have scaled up, and we can deal with more or less important volumes of data. And then we are moving towards much more ambitious solutions in order to really reach what we talked and what you have read about big data. Okay. So comments or questions before we stop here? Okay, so good. So I'll see you tomorrow for the second part of NoSQL, and have a nice Friday. We're happy because it's Friday, even if tomorrow we still have to work a little bit. Au revoir. À demain.